Hey everybody, welcome to the Math Magician's Den. We are here again today to talk about limits, and we're going to just do some basic properties for limits. Let's talk about this first theorem that I've got on the page here. Theorem 1.1, some basic properties for limits. Now, we're going to let b and c be real numbers, but we're going to let n be a positive integer, okay? What is the limit as x approaches c of b? In other words, what's the limit of a constant? Well, let's take a look at the example we have here. The limit as x approaches 4 of 6. What does y equals 6 look like? Well, y equals 6 is just a horizontal line. And if you go to x equals 4 and you look at the limit as you get closer and closer from each side, it seems to be to me like they're all the same value. So the limit as x approaches 4 of 6 is going to be 6. So what's the limit as x approaches c of b? Well, the limit of a constant is just a constant b. Now, it gets a little easier here when we start talking about x's. The limit as x approaches c of x. Well, we talked in earlier lessons, if you've watched some of my other videos, one of the things you can do with limits, if it's a continuous function, if it's a well-behaved function, you can just plug in the number. So what's the limit as x approaches 4 of x? Just plug in the 4. The limit would be 4. So it's the same thing over here with the limit as x approaches c of x. You're just going to plug in c. Go down the line here. When you talk about the limit as x approaches c of x to the n, plug in the c. It would be c to the n because x to the n is a power function. Power functions are continuous everywhere. So you can just plug in the number. So what's the limit as x approaches 4 of x squared? You're going to plug in the 4. And so my limit there would be 16. So some limits aren't as hard as we make them out to be. Now, down at the bottom of the screen here, we're going to let b and c be real numbers again. We're going to let n be a positive integer. And we're going to let f and g be functions where the limit of f is actually L. And the limit of g as x approaches c, all of these are going to be x approaches c on the left. All of these are going to be x approaches 4 on the right, just for these problems here. The limit as x approaches c of g of x would be k. So what happens when you take a constant times a function? Well, what you do is you take a constant times the limit of f of x, which would be L. So notice over here, I already know what the limit of x squared is. I did it up here. The limit of x squared as x approaches 4 is 16. So this problem here, if we're multiplying x squared by 6, I can take 6 times the limit. And 6 times the previous limit is 16, so that would come out to be 96. Now, what happens if I do f plus g? Well, you would take the limit of f, which is L, plus the limit of g, which is k. It's the same thing if you subtract. What is subtraction? It's just adding a negative. So if the rule works for addition, it's going to work for subtraction. Now notice, what's the limit of 6x squared as x approaches 4? Well, I just found that. That's 96. And what's the limit of x as x approaches 4? Well, I found that up here. It's 4. So we're going to take the limit of the first function plus the limit of the second function. This actually comes out to be 100. So far, so good. What's the limit of f times g? Well, you're right. It would be L times k. So when we're looking at this limit here, if I have two separate functions, I can take the limit of x squared as x approaches 4. We already know from above that was 16. Now, when we talk about roots, the square root of x is a continuous function at 4. So we can just plug in 4. This would be 16 times 2, which is 32. Now, we've got to be real careful when it comes to division. When it comes to division, I always have to think about the bottom and the bottom not being 0. So you're right. If you've already figured this out, the limit as x approaches c of f of x, it would be L on the top. It would be k on the bottom. But we have to specify that k cannot be 0. You can't divide by 0. Otherwise, that limit's not going to exist. So when we look over here at the example 4, the limit as x approaches 4. The top we already know from the above example is 96. And we just did the square root of 4 right here. We figured out that was 2. So my limit here is 96 divided by 2. It would be 48. I hope this is all making sense to everybody. One more here. F of x to the n power. If you take a function to a power, the rule is you can take that limit to that power. So what we're going to be doing over here, we know the limit of x squared is 16. So I've got to take 16 to the third. Now, that's not an easy thing to do. Most people are going to use their calculators. Okay. It comes out to be 4,096. So you can see how these basic rules for limits, if you have well-behaved functions, this can work out really well. Now, we're going to talk about some other properties of some simpler functions. Let's talk about polynomials and rational expressions. Now, one thing we know about a polynomial. Okay, let's let p be a polynomial function. Let's let c be a real number. Okay, and we're going to talk about the limit as x approaches c of p of x. What is the limit of a polynomial? Well, a polynomial is continuous everywhere, so it is well behaved everywhere. So all you have to do with polynomials is just plug in the number. Your limit is just going to be p of c. Now, what happens if I do a rational expression? Well, a rational function is given by p of x over q of x, and p of x and q of x are both polynomials. Okay? And sorry about my typo here. This should be given by. And now p of x is a polynomial, and q of x is a polynomial, and we make sure that q of c does not equal 0. Then the limit as x approaches c of p of x over q of x. In other words, we're finding the limit of r of x. It's just going to be p of c divided by q of c. We're just going to plug the number into the rational function as well. Now, when we talk about, sorry, I like to use different colors. The limit as x approaches 2 of this polynomial function. All you have to do is plug in 2. So this would be 2 cubed plus 2 times 2, minus 4. So this would be 8 plus 4 minus 4. The limit would be 8. Pretty simple. Same thing on the next one. X to the 5th plus 4. That's a polynomial function. We just plug in the 2. 2 to the 5th plus 4. So this would give me 32 plus 4. My limit would be 36. Now, just as an example here, when you guys take a look at this rational function, we already know the limit of the top. Well, it's the green. It would be 8. We already know the limit of the bottom. It would be 36. And that reduces. Divide both by 4. That reduces to 2/9. There's my limit. Okay. Now we're going to keep going here. Let's talk about some roots. Radicals. Now here's where things get a little hairy with radicals, because odd roots, I don't have a problem. Okay, let n be a positive number, and let's let n be a positive root. We're never going to have negative roots. Okay. The following limit is valid for all values of c if n is odd, but it's only valid for c greater than 0 if n is even. And now the reason we say that is because we can't take the even root of a negative number. So over here, this first example, if we're going to do the cube root of x, I can certainly plug in 27, and the cube root of 27 is 3. That would be my limit. But what if I wanted to take the limit as x approaches 27? Let's make it negative 27 of the cube root of x. So that would be the cube root of negative 27. Well, guess what? That works. That comes out to be negative 3. So with odd roots, you can plug in positive numbers, you can plug in negative numbers, because odd roots are continuous everywhere. Now, when it comes to even roots, the limit as x approaches 16, well, the fourth root of x is continuous at 16. So I can just plug in 16, and the fourth root of 16 would be 2. Now, what if, I'm going to write off to the side here, what if the limit as x approached negative 16 of the fourth root of x? I wanted to write fourth root there. Well, the limit as x approaches 16 of the fourth root of x would be the fourth root of negative 16. The limit, that function doesn't even exist at negative 16. So this limit does not exist. It's not even in the domain. And let's talk about one more idea here. Okay, let's talk about composite functions. Okay, with this composite function, what we're saying is, if the limit of g of x as x approaches c is L, and the limit as x approaches L of f of x equals f of L, then you can do a composite here. In other words, the limit of g comes out to be L, so the limit of f of x is going to be f of L. Now, let's do the bottom number first here, this bottom example. What's the limit as x approaches 25 of radical x? Well, it would be radical 25 because it's a continuous function at 25. And my answer would be 5. Now, what's the limit as x approaches 4 for x squared plus 9? Well, that's a continuous function, so well behaved. You can just plug in the 4, and I get 25. Now, think about this. If I had a function where I plugged this function into that one, wouldn't I plug the result of this limit into that one to get the final limit of the composite? So when we're looking at this composite function up here, we do the inside first, which is 4 squared plus 9, just like I did here. That comes out to be 25. And then you can think of it as, hey, I'm doing this limit right here. The square root of 25 is 5. So just some basic properties for limits here. I hope this helps. If you guys like this video, please hit the like button. If you feel like this is helping you with your math, your calculus, feel free to subscribe to my channel. I appreciate it. I'll be putting up more videos later on.